Thank you very much for introduction. And それでは、まずは私、山本。
So let me start with me, Yamamoto. I will talk about chemistry. And in the latter half, Enrico, my colleague, will talk about AI and other hot topics. So let me start. It's entitled Quantum Error Corrected Computational Molecular Energies. So this is about end-to-end. So it's about chemistry, estimation, and error correction. So with this combination, what can we do and what we plan to do in the future? I hope that we can think about this together. And this is a very hot topic as well. Why? Because the paper has been uploaded in the archive today. And it says in preparation, but it is now able to access. You're able to access in today's round. So if you're interested, please search under this title. And what this paper is about, as Osawa indicated here. So we have this chemistry, algorithm team, software team, and hardware team. They, as a global Quantinuum team, worked on this end-to-end chemistry application. Do you know error-corrected chemistry computation? Do you know how far ahead that would be? When I first started this area, error correction just started. So, I was just told to do the best you can. But if you look at the result that I will explain after this, the future isn't so far away. So let's look at why this quantum chemistry is so promising. I know that a lot of the speakers have already talked about this, so I will be brief. But in terms of quantum chemistry, I think it's promising as a killer application for two perspectives. One is, if you calculate it just using supercomputer, HPC, then basically the computational cost is exponentially large. So there's some limits to what can be computed. And the other is that if you use quantum computing, if you use this algorithm, you will be able to gain advantage. So there's an expectation for exponential computation. And then, what about quantum computation? What is this? In quantum algorithm, and they're securing exponential speed up in different algorithm. And by using this algorithm, if you use quantum computation and if you do quantum chemistry or phase estimation, you'll be able to measure this energy better. So you will get the desired precision of the energy estimate. So if you use this algorithm, and if you want to draw out a meaningful result, I believe that you will definitely need quantum error correction, QEC. But this is an area that's difficult to be implemented today. So what we decided to do is to actually use all the expert layers of the continuum to see what we can do in terms of end-to-end chemistry workflow. So in Quantinuum, we have in Quanto, this is a chemistry calculations. It's a circuit design compilation tool, and then you have hardware H2. And then you have the ticket for building and encoding the QPE circuits. And if you implement this, what does it look like? And I'm going to show you the slide just so that you can get an image. So upper half, you can see logical circuits. So this is the relatively simple logical circuit that would be necessary for what you would be testing. And if you were to do encode with QEC, this is what it looks like below. Redundancy has been implemented, and you utilize redundancy to detect error and correct error. So there's an overhead as a result of that. If quantum computers' performance is so high, so this the attempt to correct error itself could become an error. So the first demonstration is very difficult, but Quantinuum has experts who understand the hardware's performance, and they have been able to extract the meaningful signal from this. So if you're more interested in technical element, I want to deep dive a bit. So in this demo, we're using a single ancilla QPE algorithm. This is called early FTQC algorithm. And we use 713 color code. This is Tian code. This is not the error detection code, but it actually detects error and corrects it. So it's a color code. And it's not just about demonstrate it, but this is because end-to-end chemistry workflow, we take 1 qubit Hamiltonian representing an H2 molecule as a simple example. And this is the highlight. I don't have the time to introduce everything, but I will just highlight the important points about this experiment. So in the demonstration of 22-qubit register, we utilized up to 2,185 physical 2-qubit gates. And there's 760 mid-circuit measurements. So we have done many quantum measurements in the middle. And we have changed the workflow, and we've done it so on a real-time basis. And what's more important is that real-time error correction functioned so that it improved the overall circuit fidelity compared to when you didn't do anything. So we were able to demonstrate it through this experiment. And I would like to see what we saw as a result of this. So we have a relatively simple algorithm called information theory QPE. And as you can see on the right-hand diagram, we were able to obtain this calculation result. So you will see the phase value horizontally and vertically. You will see the probability of where that phase is. And starting from the top, the lesser the shot, there's less material. So there's a lot of dispersion, but if you increase the number of shots, so if you go 100, 500, 1,000, 1,200, 2,300 shots, then the signal becomes sharp. I think you can see that. And so far, the signal is still visible. So in terms of energy estimate, it does not fulfill the criteria for quantum chemistry. But as we improve software and hardware, we can accelerate the energy estimate. So, in conclusion, we did a demonstration of end-to-end chemistry workflow with phase estimation combined with error correction. And for the rest of the information, if you could just read the paper, I would appreciate it. So that is all for my presentation. And now I will hand it over to Enrico. And he will talk about AI.
Thank you very much, Kentaro. Now I want to switch gear, and in the next 10 minutes, I'm going to show you what we are doing at Quantinuum. Here are some acknowledgements for the work that Kentaro and the team have done. And I want to talk about what we are doing at Quantinuum to accelerate both quantum and AI. And in this context, I want you to look at quantum and AI as two sides that are working alongside in a synergistic effort to define a new computational paradigm. We're putting together the good computational capabilities of AI that everybody is experiencing right now with the powerful computational capabilities of quantum computers. And we're doing this in a way where quantum and AI will work in a feedback loop and reinforce each other along the way at each iteration. However, even if you take these two sides independently and you only look at each half of these two arrows, you will see in my next slides that you actually get and discover new value and new results. For example, let me just look at the bottom half of this feedback loop, where we are enabling the next generation of quantum computers using the current generation of AI models. This is usually called AI for quantum. And it's an exciting research direction that many people are exploring right now. And in particular, we are using it at almost every level of our integrated full stack, from hardware calibration to circuit compilation to quantum error correction decoding, and all the way to the final top layer of the applications. In this context, I just want to highlight what Quantinuum and Google DeepMind have collaborated on, and that was recently published in the Nature Machine Intelligence journal. This project shows the symbiotic relationship between quantum and AI that I was talking about. And in particular here, Quantinuum and Google DeepMind work together on a deep reinforcement learning algorithm where state-of-the-art AI was able to optimize quantum circuits and discover new ways of compressing those quantum circuits and reducing the resources that are needed to run these quantum circuits in the future fault-tolerant quantum computers that we expect to have at the end of this decade. On the other hand, you can look at the top half of this feedback cycle and see how, for example, a new generation of AI models can be enabled by using quantum computers and quantum algorithms. This is what people refer to as quantum for AI. And in quantum for AI, the paradigm is to use quantum algorithms and new techniques that are not available in the classical world to mitigate some of the drawbacks or challenges of the current generation large language models. For example, the fact that they use a large footprint of energy and they're also very hungry for data. This kind of development in algorithmic research led us at Quantinuum to define QuickSER, which is a quantum transformer model. You can think of it as a quantum sibling of ChatGPT, at least the high level. And what it does is it ingests classical data, for example, sequences, and then it uses quantum algorithms to come up with an answer for the task that you want to solve, for example, some natural language processing task or some classification task. And the aim of this research here is to define new type of machine learning models based on quantum algorithms and quantum computers that can be more efficient and more performant. For example, use less data to reach the same accuracy. Now, what can we do instead when we put together these two halves of the cycle and we let quantum and AI work in synergy? So we take the most powerful quantum computers and we take the most powerful classical AI and we make them work together in a feedback loop. And at Quantinuum, we have defined a new framework called Generative Quantum AI, or GenQAI for short, We have introduced this at the end of this year, and recently we put out a blog post where we showed some of the results that I have in the next slides. The core idea of GenQAI is to have quantum data from powerful quantum computers that are difficult to simulate classically to train an AI model that can then learn and be informed about what to run next on the quantum device and keep this loop reinforcing itself. I want to show an example where this generative quantum AI framework is put at work for a very specific application, which is in quantum chemistry. And that's the same application that Kentaro showed you in the previous part of the talk. In this case, we are focused on the so-called generative quantum eigensolver to find the ground state of a molecule. And we have integrated this generative quantum eigensolver into Quantinuum full stack, going from quantum chemistry software that was already introduced by Kentaro, all the way to our cloud operating system that orchestrates all the quantum circuits run, and all the way down to our Quantinuum systems, emulators, and hardware. The data generated from this system here is used to train a sequence-to-sequence model or a transformer model, which then generates new circuits that are going to be better circuits to solve our task of ground state preparation. And these new circuits can then go back and be run on the hardware to create the ground state of the molecule. This loop here was actually performed for the first time at Quantinuum just last month. And we created a data set directly on our system H11. And this data set was running a bunch of circuits through Quantinuum Nexus and measuring the energy of the state prepared by these circuits for the hydrogen molecule. This was a proof of concept demonstration and a benchmark test for our full pipeline. And just based on the data generated from our device, a transformer model was trained only on this generated data and was able to create a new type of circuit that when we run on the quantum computer was able to get to the energy of the ground state, even though the energy of the ground state was not included in the original data set that we got from the quantum computer. So the machine learning model learned from the data and got better at creating new circuits that can solve your final task. Now, how are we confident that the data generated from quantum computers is something new that the AI cannot get otherwise? How can we make certain of that? And in order to be confident about it, we benchmark our quantum computers and we improve their performance year by year and generation by generation. And over 5 years ago, we made a promise that we would actually improve our quantum computers, in particular, looking at the metric of quantum volume, by a factor of 10 every year. And we have now delivered this promise. From 2020 until today, in 2025, we have increased our quantum volume by a factor of 10 or more. And we recently announced this week that we reached a world-leading quantum volume of 8 million, or 2 to the 23. So we are confident that our quantum computers, the current generation and the future generations, will be powerful enough to create data that is currently not available from classical devices and can be used to train machine learning models that will then solve important tasks that cannot be solved classically. Thank you very much.